Yep.
If you replace, I mean, it probably has nothing to do with your problem, but if you replace trivial residue extension for the valuation with, for example, separable, the same problem makes sense, right?
The same problem makes sense. I haven't really thought about it, but yeah, I mean, certainly, right? Certainly, I mean, if you do local uniformization, then normally you don't impose this this condition that the valuation is rational in this sense. So it makes sense to generalize from this. Yeah, it hasn't really. I can't see whether this whether this version implies the one with separable instead. But yeah, I mean it's plausible that again there should be some sort of preservation of difficulty going on. But I haven't really thought about it. Okay. Yeah, I should say, I mean, in fairness, I mean, we weren't the first people to make this connection with resolution of singularities. There's also some other work. So there's a paper in the early 2000s by Denef and Schoutens where they work out exactly this existential theory with the parameter t, and they use full resolution of singularities. And there's also some recent work, roughly contemporary, by Konstantinos Kartas, where he works with quite general valued fields, but he uses quite a strong resolution assumption to get results in that. So there's a bit of, there are other people who looked at resolution and the model theory of valued fields. What's next? I've not, in fact, come to talk about this paper, appearances notwithstanding. There's still one hypothesis. There's a separability hypothesis here, and sort of it turns out that I care about this separability hypothesis, or rather I find it annoying. Let me first observe that the separability hypothesis is really necessary. So that's, I guess, an example. And I work over the field FPS, and I look at a couple of valued fields. I start with K0, which is just, I'm switching here my letter for the uniformizer. It's pi now, C double parentheses pi. K1 is K0 adjoin a pth root of pi. K2 is K0 adjoined a pth root of pi plus s. Sorry, that's not pi, that's s in fact. And K3 is K0 adjoined a pth root of pi squared plus s. Well, I guess I should require that p is greater than 2 for this to make sense. So the idea is that this is certainly a complete discretely valued field, and that's the valuation I'm going to carry around with me. This has residue field C, and then K1, K2, and K3 are finite extensions of this field to which the valuation extends uniquely, and the residue field of all three is C adjoined a pth root of S. Yeah, I think it's clear. If I join a pth root of S in the field, I certainly also adjoin a pth root of S in the residue field. But if I take these other things, because pi has positive valuation, the residue field extension is the same.
No, I am confused about R4. Don't you need the implication in the other direction?
Sorry, where is, I mean, for all. Sorry, this was.
Yeah.
That was confusing. So what I claim is now I have, here in this example returning, I have three valued fields containing C as a trivially valued subfield. They all have the same residue fields, but they don't have the same existential theory. So K2, K3 have distinct L-val C theories, and in fact, if you work harder, you even get distinct L-ring C theories. Why is that? Well, I mean, the first one is very simple. K1 contains a p-th root of S, and the other two do not. So that's, I think, a very simple way of saying that.
And the same with pi plus S and pi 2.
Pi is not in the language. Be careful.
Oh,
yeah.
Sorry, yes.
So that's our point. Yeah. So clear. P-th root of S is not in K2 and K3. And for the other, I can, for the moment, write down something very kind of unmotivated. So K3, V3 with its, K3 with its natural valuation V3 satisfies a certain sentence, namely, there exists R and R prime, such that R is not in the valuation ring, and S minus R prime to the P times R squared is in the valuation ring. Okay, I mean, I've written down a sentence and I claim it's true in K3. You can work out what the parameters need to, how you set these things. Namely, you set R as 1 over P, and R prime is a p-th root of pi squared plus S. And I claim this sentence is in fact not true in K2, and so I've found that the theories differ. But of course, at the moment, this is completely unmotivated and doesn't tell you anything.
But in fact, to show that your separability assumption is necessary, it would be sufficient to have K1 and K2.
Yeah, of course. Of course, although that's perhaps a bit silly because maybe I could get away with requiring K over C to be separable. So what are we going to actually do? Well, we're going to prove theorem D. I mean, I'm not going to get rid of R4, am I? So let's do theorem D. This is, I guess, 25 plus. I've not quite finished writing the paper, but certainly should be in the archive before the year's out. And the idea is everything is the same, except instead of this hypothesis, I assume that the valuation rings over C are formally smooth. I don't assume that everybody knows what formal smoothness is. Suffice it to say, I mean, this is a condition from commutative algebra or topological algebra even that's studied in EGR to develop some material on smoothness of schemes. For those in the know, this is a topological condition, so I'd better tell you what the topology is. It's the adic topology induced by the maximal ideal here. That's really the only sensible thing you can do for local ring. But I'm really happy for the moment to treat this as some kind of abstract condition instead of telling you, I mean, this is defined through some sort of lifting property. And I really want to, work with this in an abstract way.
And you still need that C is trivially valued?
Let me say I choose to work in the setting that C is trivially valued. So I should say in this original paper with Sylvie and Arno, we treated the case that I guess C is a discretely valued field in the literal sense of value group exactly Z and defectless. And that's somehow a case we really completely cleared up. Well, I guess the residue field extension had to be separable again. But somehow it's really important that C is either trivially valued or has value group Z. And given that we did this in the other paper, I'm just using the trivial case here. Anything else should be harder again if you don't require your ground field to be discretely valued to have higher rank, say. This should be harder. Let me give a couple of properties and examples. First property is that if the residue field extension is separable, then we have the formal smoothness property. So, in other words, this is a true generalized. This contains the previous theorem as a condition.
Maybe you should change the chalk. I think.
Let me go to the other and try harder. So this generalizes the previous theorem. It's sufficient to have residue field separability. On the other hand, I guess I should also, in all honesty, say, let me call this 1 prime. The converse holds unless V has a uniformizer. So really, the interesting new case for me only applies to valuations that have a uniformizer. Then I will get new results here. Secondly, at some point I want to tell you the theorem already tells you of these three fields, K1, K2, K3, at most one can have formally smooth valuation rings, because I told you they have three different existential theories. 2 kills one of them, namely if OV over C is formally smooth, that implies that K over C is separable. So this time, the first thing was about the residue field. This is about the valued field itself. So in particular, we learned that K1 is definitely not formally smooth. So K1 is a bad field that doesn't fall under this umbrella.
So what do you mean by has a uniformizer that it's
the maximal idealist principle?
Oh, okay.
3, I'd better give you some. I haven't yet convinced you that.
It's not discrete valuation, but it's the smallest positive element or something.
That's all.
Like that.
That's all. Yeah.
Okay.
That's all. Third case, I'd better give you some interesting examples of where this happens. And this is, I guess, let me state this in slightly gratuitous generality. For V over C, a smooth variety, take some point of codimension 1, the local ring at that point is definitely a discrete valuation ring, and I guess, I can, but I don't need to complete it or henselize it or whatever. This is formally smooth over C. This is how we produce some, smooth things are formally smooth, hopefully unsurprising. But let me give you some actual examples in this vein. Let's again work over the field FPS. Let's consider adjoin one more variable and let V. I want to write down a valuation on F which is trivial on C, and I'm going to use the T to the P minus S added valuation. Okay, so that's it's a valuation associated to some irreducible polynomial over the field C. That gives a valuation. OV, and I guess also OV hat, are formally smooth over C. Well, that's just the previous example for the affine line. Yeah, I mean, F is the function field of the affine line. The affine line is my favorite smooth scheme. I've taken some closed point of codimension 1 on this smooth scheme. Its local ring is formally smooth. Okay, so this is an example of a genuinely formally smooth valuation ring, but its residue field well, I've adjoined a pth root of S. That's because I've worked with respect to an irreducible polynomial. If you stare at it for long enough, you'll realize that this thing, or rather, I mean, its completion, is exactly the field K2 over here, if you map it to the right thing. So the point is that the field K2 here is the good one. K1 and K3 are both bad. Yeah, so that's the K2 is the one to which this theorem somehow applies. I've still not said anything that would justify why I cared so much about removing the separability assumption, and what I can get from that. So that's point 4, which, I mean, not really, but morally are somehow non-standard versions of 3. Let me state this in somewhat restricted generality. Let C be equal to little k adjoin S, or really the function field of a curve over little k. The curve, I mean, that's the projective line again, but it doesn't really matter what curve you take. And take some non-principal ultrafilter on the set of places. So the set of closed points of the of this projective curve. Then the field where take the ultra product over places and take the completion, say, I guess I don't have to, but I will, as valuation ring formally smooth over C. Yeah, so that's a non-principal ultra product of completions. Sanity check. The field C certainly embeds into this ultra product because it embeds into each of the factors, but C in fact embeds into it as a trivially valued subfield, basically because any element of C only has finitely many valuations where it will be non-zero. So in the ultra product, all this goes away. Now, C embeds into as a trivially valued subfield into this thing, and the claim is the valuation ring is formally smooth over C, and you should think of this, I mean, not really, but it's somehow related to 3 and under an ultra product. And now 4 is really the example that motivated this entire endeavor, because, well, the residue field is just the ultra product of the residue fields. And that's usually not separable over C, because, say, if little k is a perfect field, then all these residue fields are going to be perfect. This ultra product is going to be perfect, but the field C is not perfect. And a perfect field is never separable over an imperfect field. So that was somehow exactly the motivation for this theorem, because we now have an existential Axe-Cauchy-Yershov result which is applicable in this kind of situation, which it wasn't before. Okay, so the now let me give some example for how to apply this. Let me, I don't think we're going to need the theorem again.
Sorry for the theorem you're erasing now.
Yeah.
You say you cannot make precise for which field you want condition R4.
Yeah. No, I think no. Sorry. For this theorem, it's in a sense easy because I guess I've already told you if my valuations don't have a uniformizer, you somehow play it back to exactly the previous situation because then everything's separable, and otherwise you need to coarsen one step. You need to coarsen precisely one step, and then you get a genuinely henselian valued discrete field with value group Z, and that's the field over which you need this R4. That's the large field that you're working with. So let me give you a proposition. Part A, assume R4, and let C be a global function field. So something like FPS. Then I give you a set of sentences, namely the set of L val C sentences, such that phi is a Boolean combination of existential sentences and holds in almost all completions. CV hat. This is decidable. Okay, let me perhaps before we comment. Let me give two variants of this that in a sense are less important.
So C is still KFS or something different?
It's a global function field.
Oh, exactly.
A prime, less important.
Over finite field.
Yeah. Under R4, same for all completions. So this is almost all. Almost all means all but finitely many, but it turns out to be the same theory if you say all but Dirichlet density 0. It's the same theory. For if you demand all completions, that also works. Without R4, still works for almost all and L ring C sentences. Yeah, maybe let me say a couple of words. So I guess model theoretically, it's somehow clear that this has something to do with 4, because deciding whether whether a sentence holds almost everywhere means holding in every non-principal ultra product. So somehow I need to check whether I hold in all non-principal ultra products, and my theorem says in are pseudo-finite field extensions of C that are well understood. So that's somehow how these things go together. We are formally smooth. We apply our theorem. We play it back to the residue field situation. The residue field situation is classical work on pseudo-finite fields, actually with some interesting twists. So one needs Chebotarev again and things like that. So that's where this comes from. But I should say that both of these are in a paper of myself and Arno Fehm in early 24, which is perhaps a curious chronology, because I've told you that the theorem on which this build is unpublished, as yet unfinished work of mine that's not yet done, whereas this has existed for almost 2 years. And so the point is that we could, in our paper, we could do this in a very ad hoc way, relying on the fact that the ground field is perfect. So somehow we didn't really understand the formal smoothness condition there. We wrote down a certain axiom that made this work, but that really relied on the ground field being perfect. And we could just write this down, and I guess for, I can now say part B, and this is, I guess, new as it were. Same for function fields over many other base fields. So for instance, let's say separable closure of some finitely generated field extension of Fp, or many PAC fields with free absolute Galois groups, and so on and so forth. So somehow there's many other fields such that I guess the field needs to be computable again for this to even make sense. A wide class of fields such that for function fields over this base field, I can decide this theory of almost all or all completions. All of this is phrased for Boolean combinations of existential sentences. The reason for that is, I guess, well, my method only really says something about existential sentences or Boolean combinations thereof. Why I phrase it like this is because this is a highly incomplete theory, so somehow only understanding existential sentences a priori does not allow you to understand Boolean combinations of them. But the method just splits it out straightforwardly. I think this is a Nunck's theorem because I guess it's natural from a sort of local global standpoint, right? That you would want to decide, is some existential sentence true in all completions? Although there's I mean, the slight snag. So I use R4 here, and I guess the arithmetic geometers might tell you, well, isn't this theorem obvious? It's somehow easy to see for smooth projective varieties. So saying for smooth projective variety over C, it's very easy to say whether it has a point over all completions. But somehow if you drop this smoothness and projectivity, it gets harder. And I guess that makes it very natural for some sort of resolution condition, even if here it's quite a weak one in the guise of R4 to pop up. Okay, yeah, I guess what else do I need to say? I mean, in this case, I said this has some, I mean, in both cases, this has something to do with I need to describe the theory of all residue fields quite explicitly. Here, this is somehow classical. I mean, we get it from the book of Fried-Jardin on field arithmetic. How do you decide the C theory of almost all residue fields? And here you do a very similar thing. I mean, you somehow, this turns out to be very annoying to write down, but basically the idea is we understand PAC fields very well, obviously model theoretically. And so here it turns out that the theory, I mean, I somehow need to describe all the finite extensions or almost all of the finite extensions of this base field that arise. And I can do this in a fairly explicit way.
Small question, you just said that on a smooth projective variety, it's easy to see whether there's a point or not on a completion?
On almost every completion.
Is that easy to see?
I mean, I guess it boils down to the fact if you have a smooth projective variety of good reduction, then you get a point on the completion if and only if the reduction has a point of the residue field. Because somehow you can reduce in one direction and you can do a Hensel lift in the other direction. So it's somewhat easy to see that you play it down to the residue fields again, and there's finitely many bad places, but if you're only interested in almost all completions, then that doesn't bother you. Yeah, so I mean, both in this setting and in our setting, you can only hope to play it back to the residue fields, but these we understand well. And indeed, they are PAC, so somehow, or asymptotically PAC, so you will always get points there. All right. Yeah, I think then that's all I wanted to say. Thanks.